Mathematics is largely about patterns, and how patterns can help you predict the behaviors of numbers. One of my favorite examples is one you may have heard of before. If you take the Fibonacci sequence, the string of numbers where every number is the sum of the previous two, and divide each number by the one before it, and then average all those ratios, you will eventually get the golden ratio, which you may be familiar with. I came across one of these patterns recently, and I found it very interesting. This pattern has to do with the squares of numbers. 1 squared is 1, 2 squared is 4, 3, 9, 4, 16, and so on. I was curious if the square numbers had a structure to them, so I started subtracting them from each other. 1 from 4, 4 from 9, 9 from 16. I quickly noticed that the differences between them were all of the odd numbers, 3, 5, and 7 for these first three. 1 is also included. 0 squared is 0, and 1 minus 0 is 1. I wanted to know if there was a similar pattern with the cubed numbers. 1, 1, 2, 8, 3, 27, 4, 64, 5, 125. When you subtract these numbers from each other, the differences are 1, 7, 19, 37, and 61. So they don't seem to have a similar pattern. They do, it's just harder to notice. The easiest way to see this is if we go a lot farther, say all the way up to 20 cubed. If we then subtract all these numbers, they still change each time, but the last digit of every number follows a pattern. The first number is 1, the second 7, then 9, 7 again, and finally 1, and then it repeats itself, 1, 7, 9, 7, 1. This is because they're following a pattern of their own. If we subtract them a second time, the numbers we get still go up, but at a quick glance, you can see that these numbers are simply all the multiples of 6. So the cube numbers do have a similar pattern to the squared numbers, only you have to do one more step of subtraction, and the final number, or final step, is 6 instead of 2. Seeing this, it's easy to wonder, does this pattern continue? Do all the numbers to the power of 4 have a similar pattern? Well, let's see. If we take 0 through 20, raise them to the power of 4, then subtract them a few times, we eventually see that there is a final step, 24. In fact, this pattern holds for every number, and while you do have to subtract more and more times the higher the power gets, you can also predict this. The number of times you have to subtract is the power you are using. For all the squares, which are numbers to the power of 2, you have to subtract twice, once to get the differences, which are all the odd numbers, and a second time to get the differences between those, 2. For the cubes, numbers to the power of 3, you have to subtract one additional time to get to the final step, 6. Using all this, it is fully possible to find out what a number to the power of another number is without directly calculating that, as long as you know what the previous few numbers to the same power are. Actually, for power x, you need to know what the previous x numbers were. I'll use 3 as an example again. For 11 cubed, you need to know both the previous 3 numbers, since it's 11 to the power of 3, and the final step, in this case 6. Raise 11 minus 1, so 10, to the power of 3, and then subtract from that 11 minus 2 to the power of 3, which is 9 cubed, which is 729. In our case, the difference is 271. Next, take that 729 and subtract from it 11 minus 3 to the power of 3, so 8 cubed, or 512. 729 minus 512 is 217. Now, subtract 217 from 271 to get 54. We know that the final step is 6, and that 54 is a multiple of 6, so we can stop here. Now that we've calculated the numbers all the way to the final step, we simply have to add together all the larger numbers of each step of subtraction. So 1000 plus 271 plus 54 plus 6 to get 1331, which we can quickly check is 11 cubed. While neat, this way of calculating powers does have a few problems. For one, it takes a lot longer than just figuring it out the normal way, but it also only works for powers larger than 2, since the differences between the squared numbers aren't the multiples of 2, but the multiples of 2, then plus 1. Finally, it requires that you know the final step, which requires that you know enough numbers to subtract enough times to get there. Fortunately, this last problem does have a solution. The final steps have a pattern of their own, which is actually a simplified version of the main pattern. To calculate the final step, rather than subtracting the previous number multiple times like with the main pattern, you simply take the power that you were trying to find the final step of, and multiply it by whatever the final step was for the previous power. For example, numbers to the power of 6 have a final step of 720, which is 6 times 120, the final step for 5. Numbers to the power of 1 have a final step of 1, which is the weirdest way of saying numbers that go up by 1 go up by 1 that I've ever heard. Ultimately, while a bit strange and hopefully interesting, this pattern of powers isn't actually useful in any way. But that's fine. It doesn't have to be. Math isn't always about finding the most important bit of information you can, just playing around with numbers and seeing what you find. And I hope that you found something interesting in this video, and thank you for watching.